What if I told you that just 1 gram of a mysterious substance could power a city for days or destroy it in seconds? That substance is antimatter, and scientists have actually made it, just not much. Here's how we created the most powerful and expensive stuff in the universe, and why we can't use it yet. Let's back up. Antimatter is like regular matter's evil twin. Every particle, proton, electron, neutron, has an opposite version. Proton, antiproton, electron, positron, neutron, antineutron. When matter and antimatter touch, they annihilate, converting their mass into pure energy, using Einstein's famous equation, E equals mc squared. That means 1 gram of antimatter plus 1 gram of matter equals an explosion with the power of 43 kilotons of TNT. That's nearly 3 times the bomb dropped on Hiroshima. Yes, we've made antimatter, just not much. In fact, over the past few decades, scientists have created about 10 nanograms of positrons and less than a few dozen atoms of antihydrogen. That's 1 billionth of a gram, created at places like CERN in Switzerland, using particle accelerators that cost billions of dollars to run.
The Large Hadron Collider is the biggest machine on the planet.
The LHC is a really big particle accelerator. Basically, it's a bunch of magnets strung together that accelerate subatomic particles to near light speed, so we can literally smash them together and see what they break up into, so that we understand what the fundamental building blocks of those particles are.
So why don't we have more? Antimatter is incredibly difficult and expensive to produce. First, it only forms in high-energy collisions, like slamming protons together at nearly the speed of light. Second, antimatter doesn't like existing. If it touches any normal matter, air, metal, even dust, it instantly annihilates. So we have to store it using magnetic traps in a perfect vacuum. No walls, no contact, just floating in a field of pure isolation. And here's the kicker. Creating 1 gram of antimatter would cost over $60 trillion, more than half the GDP of the entire world. Because the potential is insane. Just 1 gram of antimatter could power a spacecraft to Mars and back. No nuclear waste, no oxygen needed, just pure, controlled annihilation energy. In theory, antimatter engines could make interstellar travel possible, or, if used as a weapon, it could level a city without radiation fallout. Which is why antimatter isn't just a science project. It's a national security issue. Countries don't want anyone building an antimatter bomb, even if it's just theoretical. Right now, antimatter isn't just science fiction. It's already saving lives. Antimatter is mostly used for medical imaging, like PT scans. In PET scans, doctors use a type of antimatter called a positron, the opposite of an electron. Here's how it works. A tiny amount of a radioactive substance that emits positrons is injected into your body. These positrons collide with electrons in your tissue. That collision causes annihilation, releasing 2 gamma rays in opposite directions. A scanner detects those gamma rays and creates a 3D image of what's happening inside your body. And at facilities like CERN, scientists are studying antihydrogen to better understand why our universe has matter at all. Because here's the biggest mystery. According to physics, the Big Bang should have made equal amounts of matter and antimatter, which would have annihilated each other instantly. But somehow, matter won, and antimatter almost disappeared. Why? That's one of the biggest mysteries in science, and I've actually explained that strange mystery in another video you can check out later.
Let's go back to the early universe. It's hot. The energy's making matter-antimatter particles.
Right.
And then they find their antimatter-matter counterparts and become energy again.
Right.
It's an energy matter-antimatter soup. They separate here, they find another one.
Right.
There it is. Now the universe expands. And as it expands, it cools. So now the energy reaches a threshold where it's not high enough to make
Like
particles
anymore.
How about the particles you did make? How about the matter that's there? Well, you had equal amounts of matter and antimatter.
Right.
They would find each other, annihilate, become photons again. So, if the universe behaved as we expected it, there would be no matter anywhere in the whole universe.
Maybe in the future. Right now, antimatter is too expensive, too unstable, and far too hard to store safely. But if we figure it out, we'd be holding the key to limitless energy, or the most powerful bomb ever created. So yes, scientists have created antimatter, just not enough to blow anything up, yet. But the fact that we've made even a few atoms shows what's possible. And maybe one day, antimatter will power the future. If you like this video, give it a like and subscribe. This is Quick Knowledge, where big ideas move fast.
So we can also think about visible light, like we see here. That visible light comes in the form of little particles that we call photons. But the energy in a visible photon is much less than the energy that an electron has in its mass. We take this big beefy photon and it's coming along with all this energy. If it hits, say, a nucleus of an atom and produce actually two particles with the mass of the electron. So one of them will be an electron with a negative charge, and one will be a particle that we call positron with a positive charge. And they're always produced in these pairs. They're produced equally. They have not identical properties, but they have these sort of mirror properties in a way. But when we come back to the universe that we live in, everything you see is made out of electrons. Everything you touch is atoms that are made out of electrons. And you say, well, where are the positrons? Because weren't they all produced at the same time? And that is a very profound question that we don't know the answer to, is why is the universe, as far as we know, made almost entirely out of what we call ordinary matter? So one of the reasons to study antimatter, we think that it's going to tell us something very fundamental about the basic properties of the universe.